Okay, so again, this is the last session for today. And the topic is nature and biomimicry as an innovation driver. So again, please welcome Prof. Audrey, everyone, and keep your spirit alive, okay?
Yay! Biomimicry. Here you go. Yeah. So we're going to start actually by talking a little bit about what is innovation and what is, again, starting from this notion of function versus molecule, which I thought it really interesting. So if you think again about this notion of function versus molecule, you have what you want is you want to have a color, have a material that's tough, or a material that's soft, or adhesive, or that cures cancer, right? So this is the function that you want to achieve. And in this context, the molecule is only a means to get to that end. So I think it's also sometimes the reason why we forget that we have chemicals behind those things, and these chemicals can have other activities like toxicity or like be polluting to the environment or be produced in a really ungreen way. So as chemists, we need to look into these molecules, but I think we also need to remember that what we want is function. So achieving function can happen via this molecule, but we can have also different types of molecules that will achieve the same function. So really, again, trying to have this drive function versus molecule is a novel way to think about chemistry. And I think what allows you to think outside the box and develop new solutions. And today we're going to see a bunch of ways in which nature does that. Nature does things differently by being creative, and we need to be attentive to that. So this is an example of the engine of a plane that was designed by Rolls-Royce. And Rolls-Royce was one of the first company to have actually developed this concept of technology leasing. So it's this idea that instead of buying a part that you put on your plane, you're going to buy the service of having the propulsion of your plane. And what this means is that instead of just selling this, Rolls-Royce is selling you an entire service, which contains, yes, the part, but also the service of the part, the engineers coming and checking on a regular basis. And what you buy is like you rent the service. And then if at some point a piece of equipment needs to be replaced, you don't pay for it. It's in a lease, right? So this is an old thing because it's one of the first company to have developed that. So it started in the 60s, and this is the leaflet that they were having at the time, power by the hour. So you buy hours of flights as opposed to buying an actual piece that you put on your plane. So this concept it was called subscription-based economy, or also leasing. We're going to talk about chemical leasing. So it's not new, it's been around for a long time, and it has this ability to focus on the function that you want to achieve rather than on the technical solution that you as a company have to provide to the customer. So as we've seen, the problem statements are important for innovation and the development of business idea. And sometimes you think you want a molecule, but in fact, what you need is a coating. So how can you rethink what you need in order to really buy what you want? So is it that molecule, another molecule, complex molecules? Is it a powder? Is it a spray? Is it a paint? You can actually try to be a lot more creative when you think about the function you want to achieve rather than the solution that already exists on the market. So this is, again, something we've seen in green chemistry. One first option is to replace a solvent for a greener solvent. But sometimes all you need to do is to rethink the entire process. Maybe you don't need this particular molecule. Maybe you need an entire different setup. So this is why now we also have, So another concept that's really important as well before we go into nature is the concept of disruptive innovation. So it's this idea that for us to think about the new idea, the new thing that is going to change the market, we cannot think linearly. We cannot think, oh, we're going to take the existing technology and try to improve it. So a good example of that is the telephone, right? We had some interesting conversations about our phones and phones in our childhood earlier in this workshop. And phones used to be powered by wires, right? We had to have a wire connecting the phones physically, and it leads to these kinds of big wires. And of course, it's not by improving the wire that you develop the cell phone, right? It's by rethinking the way you transmit information. Instead of transmitting it through a wire, you transmit it through electromagnetic waves, and now you can actually, or radio waves, and now you can actually use mobile phones, right? Another good example that we cite all the time is that we did not invent electricity by improving candles, right? We did not invent cars by improving horses. So, you can go on and on. These disruptive innovations are important because, of course, they are central to the technologies that we have right now. It's very challenging to do. There are many disruptive innovations that actually never made it, right? We don't talk about them. We don't even know what they are, but the ones who work actually changed our lives. So here are some examples of some of the ideas that are out there, and they're quite thought-provoking, and they're meant to be thought-provoking. I mean, I'm going to also give you along the way some of the disadvantage of doing certain things this way, but they're just meant here to be examples of how you can think differently about these problems. So we spoke about the fact that we make coffee and we want to extract the caffeine from the coffee to enjoy drinking coffee before going to bed without spending a sleepless night. That's very nice. But how about we grew coffee that doesn't even have caffeine in it, right? We could do that by using genetically modified plants, right? So that's one example of what you could do. Maybe you don't want to do GMOs, so that's one thing, but that would be one way of doing a disruptive development on that. You don't like to use dyes. They're very wasteful. They're very toxic. How about we grew cotton that's already colored? And now we could use these ones from nature itself, again, by engineering nature to do what we want. How about instead of using detergent, we use self-cleaning clothes? And then we put PFAS in our clothes and we have another problem, right? So we have to be careful. We have to be careful with what we do. Again, think green chemistry. You would have to run metrics to see which one is truly better amongst the two that you have here. But again, by exercising your mind to thinking about disruptive ideas, you may also find a much greener way of doing something. Same idea here. You don't want to keep mowing your lawn? How about a no-mow grass? So I imagine this is a grass that stops growing at a certain height. That's very nice. But another idea is to stop mowing your lawn anyway. And we have a big campaign in Canada right now to let your grass grow and have flowers in it so that you can actually favor bees and butterflies and stuff like that. So that's another disruptive technology. It's like, let's stop mowing the lawn altogether, right? We are we are coming out of COVID, right? That was not a nice memory for many of us. We had to keep using, of course, pandemic COVID, yeah. We had to keep using something to disinfect our hands, but how about we use copper, for instance, as a material that has natural antibacterial properties, and how about we use that to make stuff? And then we run into the question, do we have enough copper to do that? It's always interesting, right? Green chemistry is complex. How do you think about all of that? So one of the things that's really interesting about all of these disruptive innovations is that if you look at nature, nature has done stuff in a very different and very disruptive way many times over. So looking at nature is also a way to have some of these ideas. So nature has been able to do colors without dyes, disinfection without disinfectants, scent without fragrance, adhesion without adhesives, dissolution without solvents, catalysis without catalyst, and transformation without reaction. I will show some examples of some of these ideas. So this is started a field called biomimicry, which is a field in which people look at examples in nature and take inspiration from nature so that they can develop new ideas. So the reason why people look at nature is that nature has been able to develop really smart ways via using, for instance, sunlight as a source of energy, using only the energy you need and not more, fitting its form to the function that it has to accomplish. Nature has no waste and actually recycles everything. Nature using cooperation and diversity. It demands local expertise. It curbs excesses from within, and it taps the power of the limits that are around us. And it does so, I mean, we have to be realistic, right? We don't have all the time that nature had to evolve all of these great solutions. So we have to be smarter than nature in a way. We have to sort of steal some of these ideas from nature. So biomimicry is not new, of course. There's a number of things that we have done using nature as an example. And for instance, the concept of the plane wing, the concept of the plane in general, I've been really heavily influenced by looking at birds. And what we know is that birds have this shape of a wing that means that when air goes through, it will have a longer path from the top than from the bottom, which is pulling the bird or the plane to the top because of fluid mechanics. Means anyone who's done fluid mechanics knows what I'm talking about here, right? So nature has been able to do certain things, especially by working at the nano level. So we only started to be really excited about nano stuff maybe 30 years ago, 20 years ago. This is when we started to have microscopes enabling us to look at that level, right? Well, we've had them for some time, but I would say microscopes that are good enough that we could do realistically and generally enough to start to make sense of it. But nature has been playing at the nano level forever and developed these absolutely amazing features. Here you can see features that are coming from the gecko fingers, features that are resembling here some carbon nanotubes that people have been developing since. We're going to talk a bit more about this, but also structural color, which is the fact of having color coming from nano-structured patterns, is really interesting to achieve color and amazing color while not having any dye in there. And also adhesives, and we're going to talk a bit more about that, that are designed on very clever molecular selection, but also hierarchical order inside these materials. So these are some of the design challenges that nature has had to tackle with: filtering, purifying, creating colors, detecting fires, inhibit fire, adhere and joining things, so adhesion, controlling pests, distributing information, and distributing electricity. Nature has been able to achieve those functions via, again, smart designs of itself. These are some of the other challenges as well that nature has been able to do. So manufacturing ceramics, we're going to talk about that. This is something that's very human oriented, but actually nature has been able to do very clever designs of ceramic materials, providing thermal insulation, remediation of the soil, and all of that nature is able to do at room temperature, using water, using normal pressure. Nothing crazy, right? And that's often by using really clever controlling of the kinetics of the reactions and using very smart catalysts, for smartly designed catalysts. So we're going to talk about that. And that's really what I was trying to get into. Janine Benius is the person who has actually coined the term biomimicry and is one of the really inspirational figure who's been developing some of these ideas. And what she says is that after 38 billion years of research and development, failures are fossils, and what's around us is the secret of survival. So this is how we can learn some of the things out there. So here are some examples of wonderful materials that natures have made. So abalones, these seashells here, they're a living factory for creating ceramics that are not quite as tough as some of the ceramics that we make, but much tougher than the ones that you would make by simply doing precipitation of those materials inside your beaker. So how is it? So you can see here, this material here is calcium carbonate, and the thermodynamic structure of calcium carbonate is calcite, and it's not that strong. But there is a metastable version of that calcium carbonate, which is called, so this one is calcite and the other one is aragonite. This one is aragonite, and aragonite is already tougher than calcite. But in order to crystallize aragonite, you need to control the crystallization very carefully. And what nature did is that it used some proteins that are sort of sliced in there that are constantly dissoluting, constantly dissolving, constantly dissolving the calcium carbonate to make sure it recrystallizes in the form that nature wants, which is aragonite. Also, between these different layers, you have some kind of a scaffold that is composed of chitin. So again, chitin is coming here. And what's really interesting is that so the scaffold here is chitin. In between calcium, the calcium carbonate is growing. Again, there are proteins there that are controlling this growth so that it's really the crystal that you want. And now you make this nanostructured layered features of these little platelets of aragonite. And what's amazing is that they're stronger than aragonite alone. Why? Imagine if you want to break this, you start to break, if you try to break this material, you have to break the first layer, and then you have to break the second layer, and then you have to break the third layer. So it requires more energy than breaking the material together. This is called, this is a design to deflect the failures. So if the failure starts, it's deflected because it cannot go through very easily. So this material is stronger than calcite and stronger than pure aragonite because of its nanostructuration. And this is a design that has been exploited since. For instance, if you think about an anti-bullet shield, it is layers of material that serve the same purpose of preventing the bullet to go through. So really acting in that sense. Minerals, if you think about ceramics that are what we have been able to do, via thermal treatment, we're actually able to make ceramics that are often tougher than these ones. But another advantage that nature has is to make these materials, the abalone nacre that you saw just before, often are a lot more flexible to actually adapt the functionality that you want, which ceramic not always able to do. I am stuck again without being able to put it around. Some of the things that's interesting too is that this requires high thermal energy. You see here that the ceramics are going to be cooked in this oven that requires like several hundreds of degrees Celsius to be produced. On the other side, you could use sol gel chemistry, which all happens at room temperature or very low heating, and provide some structuration, for instance, aerogels that have holes that you can control very nicely. You can control what they look like and how they are. Thank you so much. Now it works. I just wanted to add one last thing, which is that one other addition of the structuration is interaction with light. We're going to talk a bit more about this. I just put a pin onto this right now. These nacres, you see the beautiful colors that it has? It is coming from this. And we'll come back to this in a second, a bit later. So this notion of making porous materials via these sol gel techniques that I just mentioned, it gave rise to the production of a bunch of mesoporous materials that are hugely helpful, whether this is for designing filters, catalysts, absorbents. So these materials are highly, highly functional and very important. And again, look at this. They're reminiscent of the of structures that we find in nature. In this case, this is diatoms that we find in nature. So these are actually fossils that we find in large quantities in sediments, and we can use them as well for certain activities. We can use them as well, but we also take inspiration for making our own porous materials. Now, adhesion. You know I love adhesion, right? So I'm going to tell you a little bit about that. So there's a fantastic animal called the mussel, everything about adhesion. So what the mussel is able to do, which is absolutely fascinating, is that the mussel has to have access to the sea, but at the same time, it doesn't want to float around. It needs to really be anchored into the rock. What's really complicated to do is that the mussel, it's a soft material, right? It's a soft body. But at the same time, the rock, it's really hard. So you need to find a way to create a connection between a really soft body and a very hard rock. And this is a very complicated problem from mechanical engineering perspective. DOPA system. So DOPA, it's this structure here which is attached to an amino acid. So this is in a protein. And you see here this the presence of these two OH groups next to each other. It creates like a biting mechanism that allows actually to attach to the surface via some so this provides a really, really tough adhesion between the surface and this. And then, because it's not over, if you just had very tough adhesion here and a soft material there, just a big wave would be sufficient in cutting your muscle here. That wouldn't work. I mean, if you ever had muscles, you know that it's very, very chewy and soft. You could imagine that it could break very easily. So what nature invented is actually also an entire hierarchical structuration here. That means that you go from a very tough material here to a very soft material there via a gradient. And that also participates in the rigidity, in a solidity of this system. Again, something really interesting, and people are now very interested in reproducing as well this material that goes from soft to tough through a little filament. The catechol structure itself that we discussed earlier has been used for designing some adhesives that we now want to that are now applied, to making wood boards. So one of the issue with wood boards is that usually wood boards are made using formaldehyde as a small molecule that can hold the wood particles together. But unfortunately, formaldehyde is very toxic. It's highly volatile as well. So it will, in plants where you make these wood boards, you would have pollution with formaldehyde that's very toxic for people. And also this could come as well to your houses. Formaldehyde is a known volatile that we found inside houses, and it comes often from wood boards. So by designing this catechol modified soy protein glue, you could make a material that doesn't have any volatile organic compound coming out of it. Again, taking the muscle as an example. So that's another really beautiful example. This is the invention of the Velcro. So this is an invention by an engineer at 3M who has been inspired by the fact. So I think the story goes that he was walking his dog, and when the dog came back, the dog was full of these little plants. I don't know how they're called, but I don't know if you have them in Indonesia. Do you have plants that do that as well? Okay. Okay, but you see what I'm talking about, right? So these are so nature is interesting, right? Because nature reproduced this solution multiple times and re-evolved it multiple times, right? So you all know that when you go in certain parts of nature and there are these plants, you can come back and having these little fruits on your they're just attached to your clothes, right? And that's because if you zoom in, you will find that there are these little hooks, shapes that are able to attach to the material of your clothes and stick there. So what this person developed, George de Mestral, he said, I'm going to invent a material that does the same. And what he did is that on the one side, he created a structure with lots of little hooks. On the other side, a structure that has a lot of little loops that the hooks can attach to. And now you have Velcro that we all use. And I also know that it's been really linked to NASA as well. Like it was a development that really was applied to astronauts because they had an issue with how to organize themselves when they're in a big whatever. So this became really an invention that people immediately saw the potential of, and it really skyrocketed. And now we have Velcro everywhere. This other example is inspired by the gecko. So the gecko skins has these textures here with multiple buds, which are enabling adhesion to the surface. And in the gecko feet, they have inspired this really interesting technology here, where you have a material that has little buds like this as well, that can adhere to a surface. And they also have inside this design a polymer that contains this bond here, a diazo bond. And this diazo bond has a really interesting property. If you shine UV light to it, it's going to change conformation and bend this way. And what this means is that upon UV light, you can have a material that goes from adhesive to non-adhesive so that you can detach it. And this is reversible. So you can go back and forth, and you can do it multiple times. So that's really a cool invention. Another example here of taking inspiration of nature is looking at the termite mound, which I don't know, do you have termites in Indonesia? Yes. So this one photo, I believe, is probably coming from Africa. But termites are really interesting animals. We take a lot of inspiration from them as well for the degradation of biomass, because they have very specific enzymes for biomass degradation as well in their guts. But here we're talking about the way they build their houses. So these mounds here, they have really intricate mechanisms for circulating air, which allows the mounds to be very cool inside, as opposed to having too much heat. Of course, this is happening in Africa, and same in Indonesia. The temperature is very high. So you could imagine that the little termites, they would fry inside there if they didn't have a good ventilation mechanism. And so this particular building here was developed with 90% less energy consumption for ventilation by having natural ventilation being built in. And this is happening via a really smart design of chimneys and holes on the sides that allows to reflect the sunlight so that it's not going to warm it too much. At the same time, cool air is brought in and warm air is expelled from the chimney on the top, with fans at the bottom also cooling the air along the way. Again, reproducing a design that was in the mound to begin with. This is another example of a cool feature from the Venus flower basket sponge, which served as an inspiration for the design of this famous structure in London called the gherkin. Sorry. So now we're going to talk a little bit about colors for a few slides. So colors was actually something that initially really marked how rich people were. Your ability to have very colorful clothing really marked your social status. If you have beautiful colors, it means you're rich enough to buy the chemicals to make them. And that's because at the time it was not made synthetically. There were dyes extracted from nature, from different either minerals minerals or animals, but often these were not very stable. So the ones that were really good had to be shipped from a long distance and, of course, were very expensive. But this changed when William Henry Perkin, in the middle of the 19th century, discovered that he could synthesize movine, this molecule here, which is a type of quinine, and he could make it the first synthetic dye. And this particular dye has a really nice, vibrant purple color, which meant that you started to be able to have really nice colors and everybody could wear them. Similarly, after that, this opened a number of different avenues for new syntheses. And you have here 3 molecules that were done along these lines at about the same time. So you have magenta here. It's called fuchsine. It was first synthesized by a French gentleman called François-Emmanuel Verga. And this became the first sort of red color dye that you could buy synthetically. For blue, there is aniline blue here. And for orange, you have alizarin, which was developed by some German gentlemen here So what's interesting about this is that it's actually a synthetic molecule that is inspired by nature, and it was the first natural dye to be actually synthesized, and it was used for dyeing fabrics as well. But of course, one of the problems is that the development of these many syntheses resulted in a lot of pollution. So we consider now that 2 million tons of chemicals are used for dyes production dye pollution worldwide every year. And in a number of countries, this is a major problem. So I don't know about Indonesia, but I know in India, for instance, it's a really big problem. Yeah, maybe you can talk about that, about the impact of pollution. And of course, a lot of the problems comes from the fact that these azo-dye functionality that I mentioned earlier, these are very much present in colors. And unfortunately, they can be carcinogenic and toxic. And for that reason, it's really important to prevent the release in the environment. So some of the ways you can actually turn it around is to find new natural colors. So I told you earlier how these natural colors were difficult to stabilize and only rich people could afford it. I think what we have to think about now is to develop these colors from nature, from abundant resources. Often food waste is a great resource for that. And do it in a way that they can be stable so that they could be used commercially in a large scale. So this is the challenge, but here are some interesting avenues for that. Lycopene, which is the red color that you find in tomato, is a type of beta carotene that has some really interesting application. You could use it as a dye. Beta carotenes in general as well are really useful colors. Of the same family, actually, astaxanthine, which is the dye that you find in a crustacean shell, is also of the same family, and it's one that you can use for coloring as well. You have here quercetine, which is I'm not sure what color it has. Quercetine, it's yellowish, and it's one as well that is envisaged as potentially a natural color. Indigo is another example that is used widely for jeans in particular. But nature teaches us that there are also other ways. So I was mentioning earlier that nacre that you find here, this is the shell of the abalone, is able to have these really nice iridescent colors coming from the nanostructuration of the aragonite in its structure. And this is happening because when light is shone onto this material, it is reflected and bounced back in many different ways, because again, these different layers mean that the light will have different paths here. And thus this creates this illusion, this optical vision here, that we have multiple colors depending on the angle that we look at which we look at the molecule. So yeah, so this is what's explained here in short. Another beautiful example is the blue morpho, sorry, which is this butterfly here that has this really stunning blue color. And this blue color is coming from the nanostructuration on the wings here. You can see it there. And it happens in a way that it will filter off only the blue and reflect the blue color only, all the other wavelengths going through this particular material, which gives this really vibrant blue color that you can see here. And that happens only with nanostructures. So contrary to our dye, now we do not need to have any toxic chemical. You can build this structure with virtually anything. As long as you control the nanostructuration, you can have color appearing. And here is some examples of structural color in nature. You have here this beautiful peacock that has multiple colors on its feathers, but also here on the little eye of the peacock feather, you have this little fish as well that has similar structural colors. This beetle here, structural color coming from self-assembly in chitin inside the insect shells here. You have these fruits here, or the snake as well here. And here is how you can reproduce that. So you may remember from the keynote yesterday that we can extract chitin as little nano whiskers. Well, these little nano whiskers, if you do your job properly, you can self-assemble them and they will start to form these really interesting chiral nematic structures. And these guys, they interact with light. And you could make iridescent materials from them based on the 3D arrangements of nanocrystals. So this particular application in cellulose has been developed by a company. I think this is something we should maybe add to the slides one day, Anomera, and they're using it for cosmetic applications to make like pigments that have iridescent colors. So that's an example of what it looks like. So if you take a wet suspension of cellulose nanocrystals, you can see here these iridescent figures, and you can make highly ordered cellulose and crystals on the glass surface, and you can see them here via macro. These particular spirals here are depositing on the surface. So it's been applicable to paints as well as to cosmetics. So some other examples of bio-based dyes that have become commercial. So microorganisms have been able to produce colors completely. Bacteria and fungi, for instance. Company are identify DNA sequence for coding the production of colors and improve their characteristics through bioengineering. Microorganism with the right set of characteristics will then be used in big fermenters, and you can generate then colorants at scale. The nutrients for these organisms are often just sugar, so you can you can often even use some waste biomass to do that. And a pigment colorant can be either isolated after the production or added directly, which will allow you to cut on resources and limit the production of waste after this. So an example of a company that is doing that, the name of the company is Spilly. This is a using microorganisms to generate different types of dyes, in particular purple dyes. And you can see here some materials that they've fabricated with this particular dye. What's really cool is that these people are really interested in green chemistry, and they're doing lots of metrics. And you can see here examples of how they reduce the footprint of the syntheses by using this approach. In particular, they've reduced by 50% the carbon emission compared to petrochemical routes to similar dyes. So this is a dye that they want to see compete with indigo, for instance. The self-healing materials is something that nature knows how to do. So, for instance, in your blood right now, circulate something called platelets, which are really important cells that if ever you cut your finger, there's going to be platelets coming here, building up to stop the hemorrhage and stop it essentially fill the hole here that was created so that you could eventually repair the skin and repair the vessel and eventually stop completely the hemorrhage. So this particular is super important in nature. It's of course applied to wounds, but also to bone breaks and so on and so forth. We all know that our body has this ability to regenerate. So this has been developed in the context of this really important problem, which is the production of leaks. So this company, Brinker, they've been developing a system to do what's called what could be called a self-seal. So this company is selling solutions for people who are handling big pipes like that are carrying either oil or water pipelines. And what they do is they put an additive inside the water or the oil that's called platelets. And what happens is that if ever a hole is formed, the platelets here are going to accumulate in that place just by virtue of the pressure that's exerted by the leak. And they will start to limit the flow that will go through the pipe so that you limit your loss and you can eventually come and repair your hole. So another really important properties is self-cleaning properties. So we discussed earlier this possibility to make self-cleaning or self-cleaning clothing. One way to do that is by making your material super hydrophobic. You can make things super hydrophobic by some coatings, which sometimes can be toxic. But in this case, what nature found is that it could simply, again, do some nanotexturizing of their surface so that they could achieve a property of super hydrophobic. So here the surface is structured in a way that there's multiple nanostructures here that mean that the water can never fully wet this material really well. And thus, the water droplet, instead of nicely interacting with the surface, now is forming a tighter drop. And we can see here that this surface is now hydrophobic, and we can measure this by measuring this angle here. So we consider that surfaces with an angle that is higher than 150 are considered super hydrophobic. It means that they really, really do not want to have a good interaction with water. And what's fascinating about this is that you achieve this property here with the material here, the leaf, that is super hydrophilic in nature, right? The leaf is made of hydrocarbons. There's lots of hydroxy groups that loves water, right? But it's simply by nanostructuring it that you achieve the super hydrophobicities. This is really, really cool. So humans have been trying to reproduce that, for instance, for making self-cleaning systems. So you can see here examples of coatings that are made to be super hydrophobic, and you can see here that water doesn't stick to it, so they're likely to not be allows it to be really to not be stained essentially. And this can be a really nice technology to be used for making your repellent paints, clothing waterproofing, alternatives to PFAS that we discussed earlier. We discussed the okay, if it's in progress, everything's cool. Again, we discussed PFAS earlier as being a big problem. This could be a solution to avoid that. And this is based on silica chemistry that, again, has nanostructuration so that they will have a high hydrophobicity, super hydrophobicity. Another thing that nature knows how to do is to minimize waste. We said it a million times. Nature always recycles what it's created. And one of the ways with which nature is creating that is by actually using chaos and lack of organization in a very creative way. So these companies, they've been designing some carpets. Do you like these carpets? Okay. Yeah, Lars loves them. Yeah. Now, they look pretty nice, but what's cool about them is that no two tiles are identical, right? So what this means is that if ever you have a stain on one tile, first of all, maybe you're not going to see it. So maybe you don't even need to, because, you know, there's if you have that. And the second thing is that if really you have a stain and you see it, you can just color fading and whatever. If you replace one tile of a, say, uniform color, it's very hard to find the exact same hue. But here, because of this mixtures of colors here, it wouldn't be seen as vividly if you replace just one tile. So that's how you could use chaos as a way to solve a problem and actually reduce waste. So this company is called Interface, and they created a product here that is called entropy. I think it's really fantastic. It's really, for scientists, it's like, it's fun, right? I like it. It's very cool. Yeah, and then this is yours to play with. What are you going to do to take inspiration from the electric eel, which is an animal that has the capacity to create these electric discharges? The here glasswing butterfly, it's has this material that has the property to be fully transparent. So this is pretty amazing. Or what else? What? That's the tardigrade. So that is a form of. So this is like a dust mite, right? Okay, but that is really like really enlarged, right? Normally, how big is it? Like a micron? Yeah. So so it can survive in outer space. It can survive 300 degrees. So with and it's not that much research on it. So it's really an interesting thing to look into, and I'm sure we can learn from that. Yeah. That's another thing that's interesting about it. I think for making like toys for kids, it actually is also a great inspiration. And yeah, so maybe you want to tell us, Lars, what the Brazil. Ah, okay. Yeah, there's this other thing where there is this you have animals deep in the sea, like in the deep waters, and they have shapes that we have no idea why. And anyway, and this one here, it's is it because of the toxicity of very toxic? Except for yeah, exactly. So this is an example of a symbiosis in nature, having, yeah, as you said, very toxic anemone, but the fish here is able to survive the toxicity by developing its own defense. So there's lots of things that you can learn from it. Again, a little saying from Janine: if the age of Earth were a calendar year, and today we're a breath before midnight on New Year's Eve, we showed up a scant 15 minutes ago, and all the recorded history has blinked by in the last 60 seconds. So this is to just remind you that we're just been here a very short period of time, and yet we need to find solutions quickly. So here is some inspiration from nature. So what we've seen so far, we've seen that if we design change from the notion of molecule to the notion of function, this gives us some ideas to think about the problem differently. So we can reconsider the problem statement and look into it with a new eye and find disruptive innovations. And then by taking inspiration from nature, we can actually solve real case problems. We could see how nature takes design as a challenge, look at biomimicry for inspiration, and biophilic design as well for inspiration. So with that, I leave the floor open to questions and suggestions. I hope this inspired you, because nature, I think, is super inspiring. And I'm sure I'm going to hear from you some great examples of doing things this way. Thank you very much for your attention. And I want to open the floor to questions.
Okay, of course. So any questions or anyone who would like to point discussions? Come on, guys. It's the last session. After this is dinner. Yes, Pak. Silakan, Pak.
Thank you, Professor Moore. Just a story, just to add to the story. There's this Japanese research group in, I believe, in Osaka University or somewhere. They use this fungi.
Yeah.
And they put this fungi in. Well, they put these proteins like rice, and this rice, the pattern of this rice is following the places in Tokyo, like the malls, the big places, places with the big, many people visits in Tokyo. So, and then they release the fungi. So the fungi, within only 26 hours, I guess, the fungi find its stable networks.
Okay.
Because they are trying to find food, right? And then so first hour, second hour, third hour, and then after 26 hour, they find their stable network, which really resemble 95% the Tokyo metro systems, which carry 6 million people per day, I believe. So this is again how the nature is so powerful, I guess. It's really amazing.
Oh, how Japanese people are better than all of us, right? I don't know which way you take this. No one's Japanese here. Yeah. Yeah, no, that's fascinating.
The thing is, we are in Indonesia, we are having this new capital in Kalimantan. So maybe as a researcher, we can challenge them, their urban planning with the fungi things, right?
I think it's a fantastic. I'm hearing you saying something very controversial here. Yeah.
No, it's a reality. It's happening right. Inspiring, right?
Fantastic. Great ideas.
Okay. Like nature, and then try to understand how they work, and then try to mimic that. That's what you say. That's really inspiring. Like something that's been there all along, but we don't really acknowledge it, but it's there, so it's very inspiring. Yeah.
So there are other like really cool design. The shark skin is also structured in a way that has been reproduced in some speedo
swimming.
Yeah, the swimming suits. So you remember the 10 years ago, like all the swimmers, they were wearing this like full body suits, and they were made with this this texture that similar to reproduce the pattern of the shark skin, and on it better. So again, it's similar idea to this high super obesity that we discussed a little. Refrigeration is really super interesting. I think that there's a lot of potential for that in the future. And right now, the challenge for you guys is right now, in order to do this, we often require a lot of like scaffolding or sort of sacrificial molecules to build the nanostructuring, and that's very wasteful. So I think there's still a lot of research to do to make better nanostructuration.
Okay. Gimana, ada pertanyaan dari Zoom juga? Atau tidak ada ya? Kayaknya. Ada? Oh, there's a question from the Zoom also.
Zoom questions.
Yes, Zoom questions also. We have about 20, yeah? We have about 20 participants.
20 questions?
Yeah. No. 20. 20 participants.
Sorry,
I know. Second day. Yes, I know.
I'm here. I'm answering 20 questions. It's okay.
You're going to reply the emails, maybe?
Yeah.
Email form. Okay. Udah? Ada. Yes. There is. Okay. Interesting presentation.
So, thank you. I just wonder how the super hydrophobic molecular can absorb the organic pollutants such as PFAS or hydrocarbon in environment. Yeah, so I love his passion for PFAS. I mean, I think it's a researcher working in this area. Yeah, so super hydrophobic can absorb. Yeah, so I think that the principle of
So just everyone, they know the question. Can I just say it?
Sorry,
Is that
sorry.
okay?
So yeah,
So
sorry.
how the super hydrophobic molecular can absorb the organic pollutants such as PFAS or hydrocarbon in environment.
Yeah, so I think that what they want to say is that can you use nanostructuration this way to try to trap selectively PFAS or organic pollutants? It's a good question. I wouldn't. So I think the idea is trying to point at can you use some kind of similar design to take out of water PFAS or pollutants. And usually what people do is they're trying to have a system for which they more have lipophilicity, and then the lipophilic environment will trap the pollutants to this. With PFAS, you would have to do the same, but with something that is fluorinated because it's the only thing that can attract the likes attracts each other. So you have people who have developed these kinds of methodologies. With nanostructuration, I don't know that, and I don't know anything along these lines, but that's an interesting idea.
To isolate, to isolate pollutants, to isolate hydrocarbon captures, especially CCUS is in the
people use membranes as well. So they will have a membrane, and the membrane will have, for instance, lipophilic properties, and then the water flows through and things will go through the membrane that are pollutants will go through the membrane. That's another way that you can use that. So it's and you could see biomimicry here because the way the body will sequester a different thing is by creating these taking osmotic pressure as the force to get things through different membranes, and that's an interesting biomimicry as well. You can think about it this way. So,
for example, how a drug interacts with its target is very specific. So if we can maybe design an artificial enzyme, well, an enzyme always does a reaction, right? But thinking about something like a natural container that is like an active target where only a PFAS enters but doesn't do a chemical reaction, and maybe the binding is weak enough so that we can extract it otherwise or trigger the expulsion of that thing, but design in a pocket, like a pocket in a macromolecule for that kind of stuff.
That's called nanozymes, and often it's linked to the concept of having a catalyst inside the pocket to start breaking it down. So nanozymes are.
So we would have to think only about the active pocket without activity, so that we can actually isolate it.
No, for sure.
Without breaking it.
But I think you want to break it down more than anything, right? Because with the quantities you make, it's very hard to recover them.
We had that conversation with Phil the other day. Phil had an idea like 20 years ago to break down PFAS into smaller molecules that were still containing fluorine, and he was talking to people in the industry, and they told him, no, don't do that. Those molecules are even more toxic.
So they're more toxic, but there are developments more recently where people are breaking it down, and they're breaking it down all the way to fluorides. So if you break it down to fluorides, then you're good. And there's been some really breakthroughs in that field in the last 5 years, I would say. So there's some really fantastic work by Will Ditcher in particular, where he's demonstrated by a mixture of DMSO and I think it's sodium hydroxide. He can actually completely unzip the molecule and remove all of the fluorines on it. And and there's this technology in British Columbia as well that was developed recently. So there's really active research in this area. What's challenging though is that the pollution is really widespread. So collecting that, treating soils that are contaminated, treating water that's contaminated, that's going to be really complicated and timely and costly, for sure. So replacing PFAS now is really essential so that we don't put more in the environment.
Okay, so there's another question. I'm waiting. Yeah, there's also another question. Boleh dikirim? Yeah. Okay. So, Prof. Audrey, how can regulatory bodies ensure that biomimicry products are environmentally sustainable throughout their life cycle?
That's a very good point.
Yeah.
And I would say again, everything that we talk about, we have to validate via metrics. So you have to go out there. You use biomimicry. This is your inspiration, right? It's you go on a chalkboard and you invent crazy ideas. And then you look at all your solutions and then you break it down one by one and you're like, okay, is this going to meet the targets I want to have for a green product? And that's really critical to do that. I mean, one of my great mentors, Bob Crabtree, used to tell me, I mean, being a good scientist is being a little bit schizophrenic because you need to be at the same time someone that has absolute passion for science, wild and completely unleashed imagination. And then the next day you need to be the guy who's going to break down all of these solutions because you're going to find that it's not working for XYZ reason. So you have to really have these two approaches here. Biomimicry is the inspiration, or other things are the inspiration. I mean, you can invent anything you want, but then when you come down to your design board, you need to also say, okay, this is not going to work because it's toxic. So I can't do that. And remember, you go through this design cycle here where you eliminate things that are not truly going to solve the problem. So you need the tension between these two things. And ultimately, when you finish your design, your product, you do your scale up, which is what we're doing right now with our kite design extraction, you actually do the full LCA on 10 kg. And then you pray that it's going to work, right? Like you should have at that point a good idea of what's going on, but you can actually now get down to real solid numbers to back your research at that point.
Do you like have any examples? Maybe like maybe again a guidebook. Maybe again we can mimic.
And another example of biomimicry,
like the regulation.
So I don't think there's any regulation applied specifically to biomimicry, and I don't think they should, because again, the biomimicry here is here just as an idea to inspire us scientists to discover new solutions. It would not make a lot of sense to invent a law that would regulate biomimicry, because biomimicry can be anything. Again, a membrane is something that resembles the way our body is filtering things. So we're not going to regulate membranes because they're based on a biomimicry system. You see what I mean? I think in and of itself, I don't think it's the way to look at it. Rather, what you can do is you could say we're going to apply metrics to make sure that we don't put out there a material that is toxic, or a material that is carcinogenic, or a material that is going to cause harm to the environment, or a material that is going to have a big footprint in terms of waste or in terms of energy use, for instance.
Okay, I think that concludes. Is there any other, anyone else?
Anyone else? Questions? We have a lot of, do you want to participate? Do you have some questions?
Now we are discussing about your presentation, so wonderful. We feel like entering the tale story, but it's really wonderful, and nothing is impossible, right? But we need good resources and also good facilities, and also how we can appreciate every step of the research results, because it's sometimes need very long time to find the final product. And for myself, I already visited Geolog Institute, belongs to Syngenta, Syngenta AG, in London. On that place, they consist of hundreds of professors and they're working so wonderful, like extracting the from the plant or the insect, is- insect insects also to find hormone or develop problem, develop product. But the step is very step by step. It's very long term, and they should apa ya, found any failures on the research or something. But that's wonderful works.
Yeah, I mean, you're right that the research timeline is long. I think that we benefit from now 25 years plus of green chemistry, and I think there are a lot of solutions out there. And I mean, we were discussing this with was really pointing that there are solutions, even including simple solution, cost-effective solutions that probably exist already to some of your problems. So I think a big thing is creating these networks that we can exchange ideas, share ideas. I think that not everything has to cost more money, and I think that if we work together, we're gonna be able to I think find better solutions. Thank you so much. Thanks for your contribution.
And maybe another question from
Merci.
Zoom. So, what is your opinion about some coloring adjusts in microplastic or marine plastic and can dissolve in environment related to biomimicry materials?
Yeah, so the coloring in microplastics is really interesting. I mean, in fact, we have a research program about this right now. So coloring in plastic is often associated with additives that are metal-based, which means, and these metals are, we think are leaching when the microplastics are being created into the environment, causing, of course, some pollution in addition to the microplastic itself. So in addition to that, the microplastic will contain also some of these metals. So if it is ingested inside an animal, it will actually it has a potential to be released in this animal as well, also causing some toxicity there. So there's lots of implications about that. In terms of biomimicry, I'm not really sure how I would relate this to biomimicry because, again, nature only uses material that will degrade. So these plastics are not a good example of biomimicry, I would say. So,
Yeah. Okay, so I think they're supposed to be separate because this is
Yeah.
inspired nature.
yeah. So the inspiration by nature is to actually try to make plastics that do biodegrade for real in nature, and we know nature has been able to develop them. You know, the PHA is really interesting. So it was discovered completely serendipitously by this microbiologist, French microbiologist, whose name I'm forgetting now. And he was analyzing these bacteria, and then he was looking at them in a microscope. And then he kept seeing that they had these big white balls inside them. And it turns out this is a polymer with polymeric properties. And the bacteria was using it as food. So it stored inside itself this polymer, and then when it was hungry, it would depolymerize it, recreate the so it's hydroxybutyric acid, and it would eat it. That's the carbon source for the bacteria, and that's how they discovered the first class of PHAs. So, but it was discovered in the 20s, and because biochemists that never talk to chemists, it's only like 20 or 30 years later that actually a polymer chemist said, "Oh my God, this is interesting," and then the research really started.
Why is there always a big wall, between
why is there always a big wall?
to integrate, right?
Maurice Lemoine, thank you so much, Maurice Lemoine. Absolutely.
Okay. Okay, I think we can finish the
Thank you
Q&A.
so
Thank you so
much.
much,
Thank you
Audrey,
so
for your
much.
presentation. Big round of
Thank
applause.
you.
Okay. So again, as usual, I will try to summarize the talk of the fourth session. So again, biomimicry itself is taking examples in nature and trying to inspire us, to develop new ideas. So as stated before by Audrey about how is its function or versus molecule. What we want is not necessarily what we need. I think that inspires. There's a lot of daily inspiration quotes right here when we talk about biomimicry. Like she gave an example, we want phone, but what we really need is telecommunications. And then that's where mobile phones come in, right? And then science have and understand nano and molecular, and that has helped us approach on understanding on nature, and then how we can again biomimic those conditions and implement it to our daily life. So she have given a lot of examples, like how the composition of aragonite, calcium carbonate, and how that affects on making we're making tough materials, ceramics. And then she was also talking about adhesion and how it is inspired by the blue mussel, the DOPA attached to amino acid, and how it is creating the adhesion effect. And then she also stated about burdock. Burdock is the what you call it? You know, the plants that is sticking to our clothes, and it's inspiring to make Velcro 3M. And then also the gecko feet, the little buds itself, it contains polymers. It is reversible. So those are the inspirations that we can use, and definitely we can implement, and we can have benefit from it. So, and also the colorings. Yeah, the colorings, once upon a time, you know, when people have limited options of colors to clothes, and that also shows someone's status, and also how we can use natural based resources to color our clothes, and even to the foods that we eat. And then self-cleaning clothes, that's something that's really cool. So self-cleaning clothes, so you don't have to wash your clothes every day, you know, and that can also apply in coating on buildings, Teflon and glass coating. So I think again, yeah, we can have several inspirations. We can look how nature and how we can use it and develop and find new solutions that we are also trying to find in our everyday life. I think that concludes the summary for session 4, everyone.